Hello, and welcome to this presentation titled Kruskal-based approximation algorithm for the multi-level Steiner tree problem. My name is Richard Spence, and this will be a joint presentation with Rayan Ahmed. We are both PhD candidates at the University of Arizona in Tucson. So before we introduce this problem, let's first review the Steiner tree problem in graphs. So we're given a undirected graph connected G, and we'll let T be a subset of the vertices, which we call terminals. So a Steiner tree of G over the terminals is a subtree that spans or includes these terminals. So note that a Steiner tree does not have to include vertices which are not terminals. So some basic facts about the Steiner tree problem. Computing a minimum weight Steiner tree given an arbitrary graph is NP hard. However, there are constant approximation algorithms for this problem. On the other hand, the Steiner tree problem is NP hard to approximate with ratio less than 1.01. So it cannot be approximated arbitrarily close to 1. So in this paper, we study a generalization of the Steiner tree problem in graphs where the vertices or the terminal vertices require different priority or level or quality of service requirements. So we call this problem the multi-level Steiner tree problem, motivated out of multi-level graph visualization. However, this problem has other names in literature, including multi-level network design from some papers in the 90s, quality of service multicast tree, priority Steiner tree, multi-tier tree, and so on. All of these problems are quite similar, even though there are some small variations in how the problem is defined. So the idea behind this problem is that we're given a graph as before, where some of the terminals have a higher priority, which we indicate by the larger circles on the left. So in this input example, we have a graph with 5 terminals of, say, priority 2, and 4 terminals with priority 1. And in the example solution, we see that the terminals that require a higher priority are connected using higher quality edges. The figure on the right gives an equivalent multi-level visualization of this solution with the input graph on the bottom. So we'll define the problem a little bit more formally in the upcoming slides. So what is a multi-level Steiner tree? So as before, we're given a graph which is undirected and a set of terminals where each terminal has a priority which is discretized to the set 1 through L, where L is the highest priority, 1 is the lowest. We say that a multi-level Steiner tree is a tree containing edges of different rates, such that any 2 terminals, U and V in the terminal sets, are connected in this tree using edges whose rate is greater than or equal to the minimum of the priorities of the 2 endpoints. So in this example, we see that the priority 2 terminals are connected using rate 2 edges, and every pair of terminals is connected using edges of rate at least 1. So how do we define the cost of a candidate solution? We'll start with a more general definition. We'll just define an arbitrary cost for including each edge with rate I, denoted by C sub I of E. And we define the cost of a solution to be the sum of all the edge costs at their respective rates in the tree. As a special case of this, we say that the edge costs are proportional if the cost of including that edge with rate I is equal to I times the cost of including it at rate 1. So we say that edge costs are proportional if their cost is proportional to the rate. And so the MLST problem is to find a minimum cost multi-level Steiner tree given a graph and terminals. So this does generalize the Steiner tree problem, which is NP hard. So we're trying to look for approximation algorithms for this problem. There is a line of known results for this problem and variants of it. In the case where the edge costs are proportional to rate, there are constant approximation algorithms. With unrestricted edge cost, there are logarithmic approximations, one given by Charikar in the mid-2000s, which we'll go over in the next slide. On the other hand, it is hard to approximate with ratio better than log n under certain complexity assumptions. This is from a paper by Chuzoy et al. So our contributions. So we consider extensions or generalizations of Kruskal's and Prim's algorithms for computing minimum spanning trees to this multi-level or multi-priority problem. We show that a generalization based on Kruskal's algorithm achieves an approximation ratio of 2 times the natural log of t, which matches the best known approximation by Charikar et al. On the other hand, a Prim-based generalization gets a bit trickier, and if you just try to generalize Prim's algorithm, it can actually perform rather poorly with respect to the optimum. Lastly, we provide an experimental comparison between both of these logarithmic approximations, one that we propose and one by Charikar et al., and we compare the quality of the solutions returned as a function of the number of vertices, number of priorities or levels, using different graph generator methods. First, let's review the log t approximation by Charikar et al. So the idea behind this is fairly simple. It's a greedy algorithm that connects terminals together by order of priority, one by one. So this algorithm considers the terminals by non-increasing priority, starting with a root vertex, and then one by one, the algorithm connects each terminal to the existing tree or the existing solution using the cheapest possible path while taking into account the different costs of each edge at a different rate. So this algorithm essentially builds a tree one by one by connecting higher priority terminals first. So this is a 2 LNT plus 1 approximation, or we'll just say roughly 2 LNT. So the idea behind this Kruskal-based approximation algorithm, the algorithm itself is somewhat different, but the analysis is very similar. The main idea is that instead of connecting the terminals by order of priority, we'll instead connect the cheapest pairs of terminals first. So while all the terminals are not yet connected, we'll first find the pair of terminals U and V, which minimizes their cost of connecting them while taking into account edge costs at different rates. Once we do this, we add the corresponding UV path to the tree and remove the lower priority terminal from the set of terminals. So once all of the terminals are connected to form a subgraph, then we can easily prune away cycles so that the result is a tree. We can do this by removing an edge from each cycle that has the lowest rate. So using similar techniques, we can also show that this is also a 2 times the natural log of t approximation, which is independent of the number of priorities or levels L. And the running time is also O of t times the running time of Dijkstra's algorithm on an n-vertex graph. So in the next part, Rayan is going to go over the integer linear programming formulation, as well as experimental results related to this problem.
Hello everyone, this is Rian, and I'm going to talk about the integer linear program to compute the exact solution of the multi-level Steiner tree problem. If we can compute the exact solution, then we can also compute the experimental approximation ratio of different heuristics and compare those heuristics. So equation 1 is the objective of the ILP. Equation 2 is the flow constraint, which ensures that in every level, we have a valid Steiner tree. Equation 3 ensures that if an edge is present in a top level, then it is also present in the bottom levels. Equation 4 links the flow variables from the flow constraint to the edge variables from the objective. And finally, equation 5 ensures that the edge variables are either equal to 0 or equal to 1. In other words, an edge is either in the solution or not in the solution. We now discuss in details all the constraints. The objective is to minimize this summation. Here, Ci prime UP is the incremental cost of edge UP with rate I. Hence, Ci prime UP is equal to CIE minus Ci minus 1E, where E is equal to UP and C0E is equal to 0. The variable XUPI is equal to 1 if UP appears in the solution with rate greater than or equal to I and 0 otherwise. The objective ensures that there is no cycle like WUXV in the solution, because if there is a cycle, then we can remove some edge and we can get another solution which is better than the previous solution. Equation 2 is the flow constraint, and we have some flow variables here. For every edge E equal to UP, we define two flow variables, FUPI and FPUI, which means that the flow can either go from U to P or P to U. The flow constraint ensures that the edges of rate greater than or equal to I form a Steiner tree over Ti, where Ti is the set of terminals at level I. Here we have two kinds of vertices. The black vertices are the terminal vertices and the white vertices are the non-terminal vertices. We select a terminal vertex as the root vertex, and the difference between the total outgoing flow and incoming flow is equal to the number of remaining terminals if the vertex is root. For example, here for the vertex R, the outgoing flow is equal to 3 and there is no incoming flow, so the difference is also 3 and we have 3 remaining terminals. If the vertex is a non-terminal like U, then the total summation of outgoing flow minus the total summation of incoming flow is equal to 0. For example, here the outgoing flow is 3 and the incoming flow is 3, which is same. If the vertex is a terminal but not a root, then the difference between total outgoing flow and total incoming flow is -1. For example, W is such a vertex, and here the outgoing flow is 1 and the incoming flow is 2, and the difference is -1. Now, if an edge is present in a top level, the edge has to be present in all the bottom levels also, and the bottom level may have some additional edges. This constraint is ensured by equation 3. Equation 4 links the flow variables with the edge variables. In other words, an edge variable is turned on only when there is a flow in the corresponding variable. And finally, equation 5 makes sure that the edge variables are binary. We now discuss the experimental results. We first discuss the experimental setup. We consider two types of edge costs, proportional and non-proportional. We consider 4 types of graph generation model, the Erdos-Renyi model, the Watts-Strogatz model, the Barbasi-Albert model, and finally the Stein-Lieb instances. The number of priorities L varies from 2 to 7. We adopt 2 methods for selecting terminal sets, linear and exponential. In the linear method, as we go from top to bottom, the number of terminals increases linearly. And in the exponential method, as we go from top to bottom, the number of terminals increases exponentially. We now provide a plot that compares the performance of C2A and Kruskal-MLST. C2A is the algorithm by Charikar et al. For non-proportional edge weights, and Kruskal-MLST is the Kruskal-based algorithm we proposed. Here, we provide the information on Erdos-Renyi graphs with respect to L, the number of priorities. For every priority, we have 190 instances, and we aggregate the information here. We provide the minimum, the average, and the maximum experimental approximation ratio for both algorithms. And we can see the average ratio decreases slightly as the number of priorities increases. The average ratio of Kruskal MLST is slightly lower than the other algorithm. Hence, Kruskal MLST is performing slightly better than the other algorithm. Similarly, the maximum ratio is also better compared to the other algorithm. We also provide the information in a tabular format to make a better comparison. And here we consider all graph generation models we used in our experiment. We provide the information for two algorithms, C1 and K. C1 is the algorithm by Charikar et al. For proportional edge cost, and K denotes the Kruskal MLST algorithm. We provide these statistics, how many times the algorithm provided a solution which is equal to the optimal solution. We provide the mean of the experimental approximation ratio. Similarly, we provide the median and the minimum and the maximum of the experimental approximation ratio. Here, best approximation reports the percentage of instances out of 1,140 that each algorithm achieved strictly better experimental approximation ratio. Best performance in each category is bolded, and we can see that most of the time, the Kruskal MLST algorithm performed relatively better compared to the other algorithm. So this was for proportional edge cost. We provide the similar information for non-proportional edge cost here. We are comparing C2A with Kruskal MLST. Here C2A is the algorithm by Charikar et al. For non-proportional edge cost. We provide similar statistics. Again, best approximation reports the percentage of instances that each algorithm achieved strictly better. Best performance in each category again is bolded, and we can see that Kruskal MLST performed relatively better compared to the other algorithm. More than that, we provide a class of graphs for which the algorithm Kruskal MLST significantly outperforms algorithm C1. Here, the x-axis is instance number and carries no meaning of time. Y-axis is the experimental approximation ratio. We can see that the Kruskal MLST algorithm have provided approximation ratio equal to 1 most of the time, which means that the solution is close to the optimal solution. On the other hand, C1 provided a strictly larger ratio. We now provide a summary. We showed that the Kruskal-based algorithm is logarithmic approximation, matching the best approximation guarantee of Charikar et al. We formulated an integer linear program for the general multi-level Steiner tree problem, which can handle non-proportional edge costs also beside proportional edge cost. We demonstrated that Kruskal MLST compares favorably to other algorithms. A natural question is whether the analysis of any of these algorithms, greedy MLST, Kruskal MLST, or C2A, can be tightened. We now conclude the talk, and we are happy to take questions.